Turning solar electricity into cooking heat is an engineering challenge. You must convert direct current into thermal energy without massive losses along the way. Recently, a consumer trend has emerged claiming to solve this with water. The pitch is that you can connect a solar panel to a home electrolysis machine, split ordinary tap water, and generate an infinite supply of free cooking gas, often called Brown's gas or HHO. Here is a standard energy model. A 1,000-watt solar array sits on the left, a cooking vessel on the right. We can bridge this gap via Pathway A, an indirect chemical conversion generating combustible gas, or Pathway B, a direct electrodynamic route using magnetic induction. To evaluate these two systems, we have to apply the first law of thermodynamics. Energy cannot be created from nothing, it can only change forms. By tracking the exact wattage retained from the solar panel to the final target, we can measure the mechanical viability of each path. When we run the numbers, adding a chemical phase change into an electrical heating process actively degrades system efficiency. This is the internal architecture of Pathway A's primary engine, the dry cell electrolyzer. Inside, a series of stacked metallic plates sit waiting for electrical current. These plates cannot be standard iron or steel. Because they are constantly exposed to water and direct electrical current, they must be milled from titanium or 316 marine-grade stainless steel to resist immediate oxidation and rust. This introduces the first electrochemical constraint. If you pour standard tap water, bore water, or even filtered drinking water into this machine, the naturally occurring minerals and salts react with the current. Within a week, the metal plates calcify, blocking electrical flow and ruining the hardware. To keep the hardware operational, the system requires a continuous supply of 100% pure distilled water, with zero total dissolved solids. However, 100% pure water is a dielectric insulator. It does not conduct electricity. When pure water is introduced to the dry cell, the solar current hits a dead end, and the molecular bonds remain intact. To force the current through the water, the system requires an industrial catalyst, specifically potassium hydroxide, or KOH. By mixing potassium hydroxide into the distilled water, the chemistry changes. The liquid becomes a highly conductive electrolyte, allowing the intense electrical current to flow across the plates and shear the hydrogen atoms away from the oxygen. Potassium hydroxide is a highly corrosive industrial chemical. It requires a respirator and thick rubber gloves to handle, as a single drop will cause severe chemical burns to human skin and permanent blindness if it contacts the eyes. Attempting to avoid this danger by substituting household salt into the distilled water creates a different chemical reaction. The electric current interacting with sodium chloride produces lethal, toxic chlorine gas instead of combustible hydrogen. A system marketed as running on free tap water actually demands the ongoing purchase of laboratory-grade distilled water and the continuous handling of toxic caustic catalysts in a home kitchen. This Sankey diagram tracks the energetic cost of Pathway A. On the far left, we begin with a solid 1,000 watts of usable energy generated by our solar array. The electricity first passes into a pulse width modulation, or PWM controller. Sending constant high amperage current into water boils it into steam. The PWM prevents this by rapidly pulsing the current on and off thousands of times per second. This switching dissipates our first fraction of energy as heat. The remaining electricity enters the electrolyzer, where we encounter the primary chemical conversion penalty. Commercial electrolysis is incredibly lossy, capping at roughly 50 to 60% efficiency. Breaking the chemical bonds of water generates intense friction, immediately bleeding over 400 watts of our solar power out of the system as pure ambient waste heat. We now have a synthesized HHO gas mixture that contains only 500 watts of our original input energy, traveling through a pipe to the stove. When that gas ignites beneath a pan, massive convection losses occur. The heat radiates outward, escaping around the sides of the metal vessel. By the time thermal energy penetrates the vessel, our 1,000 watts is reduced to barely 300 watts. The laws of thermodynamics dictate that converting electricity to a chemical vector and back to heat will inevitably dissipate roughly 70% of the initial input energy as pure waste. The gas that does manage to reach the combustion stage presents an entirely different physical hurdle. When HHO gas ignites, it produces a high-velocity, blindingly bright blue microflame that acts like an industrial cutting torch. This split-screen chart contrasts the flame profiles of these two fuels. On the left, standard liquid petroleum gas creates a wide, dispersed shape. On the right, the HHO flame holds a tight, needle-thin profile. This shape is driven by energy density. LPG contains 46 megajoules per kilogram, while HHO reaches 120. Consequently, an LPG flame burns around 1900 degrees Celsius, whereas the HHO microflame peaks at 2800. To manage this intense combustion without the flame traveling backward through the fuel line and detonating the machine, an event known as flashback, the system requires highly specialized microhole burners and a water-based security barrier called a bubbler. But for culinary application, this high-velocity 2800-degree flame fails to deliver thermal flux. Instead of evenly heating a wide surface to simmer a liquid or bake a flatbread, it causes severe point heating, scorching a single spot or melting straight through the metal vessel while the edges remain cold. HHO gas behaves like an industrial welding tool, making its physical properties violently misaligned with the broad, even heat distribution required for cooking. This is our original two-pathway schematic. If we bypass the chemical phase entirely, we can drop pathway A and run a single, direct line from the 1000-watt solar array to an induction coil beneath the cooking vessel. This is pathway B, magnetic induction. It is a direct electrodynamic route for thermal generation. Instead of breaking water molecules, the system uses alternating current to generate a high-frequency, oscillating magnetic field. These magnetic field lines penetrate the iron or steel of the cooking vessel. As the magnetic field fluctuates, it induces localized, swirling electrical loops within the metal itself, known as eddy currents. Because the metal has electrical resistance, these eddy currents struggle to flow, generating intense heat directly within the atomic structure of the target mass. There is no open flame and there is no heat loss to the surrounding air. Because the vessel itself becomes the heat source, direct Joule heating yields an energy retention rate exceeding 90. The core engineering principle of system elegance states that the optimization of any architecture is achieved purely by eliminating intermediate steps. Converting solar electricity into chemical gas just to burn it for heat is a redundant, fatally lossy loop. True engineering optimizes the path from generation to application as directly as physical laws allow.